Okay, so you see that from the interface, there are lot of things that FRACPRO can do. We can carry out fracture design, we can carry out fracture analysis, we can carry out production analysis, economic optimization after our hydraulic fracturing, and all of that. We can export the data, we can import other data and analyze it, we can generate the report and all of that. So there are so many other things that FRACPRO can do. Basically, these are the operating modes that we have in FRACPRO. These ones are just utilities, how we can input or export data at the end of the day. But these are our operating modes that we can have in FRACPRO, either to design or to analyze fractures or to carry out production analysis or economic optimization of hydraulic fracturing activities. Of course, we cannot do all of it. We'll just do some few analysis. Then from there now you can pick it up at your own leisure time to go deep into the software to see exactly what you can do with the software. So we are going to start with fracture analysis. We are going to start off with fracture analysis. That's what we are going to do. We want to analyze our fracture. We want to do some fracture simulation to see how it looks like. So on the first part, on the first page of the fracture analysis, we have so many questions that have been asked. You have to put the field, you can put the field, the well name, the well API number, the well location, the lats, the longs, the latitude and the longitude, the formation name, the stage information, perforation details. You can put your perforation details, your treatment date, to put the date of your treatment, the company name. So there are so many other informations that we can always input here. All of these information, they are just general information. It doesn't affect your simulation anyway. It doesn't affect your simulation. If at any point in time you don't get me, make sure that you indicate that you can't hear me. All right. So if we have any information here, we can put, but we will not need to bother ourselves with all of these. So we'll go to next. All right, so under our main option here, we have fracture analysis F4 function. Under the F4 function, we have some three things that we have to define in order to be able to do our simulation. We have first thing, what do you want to do? Is it a job design? Do you want to design a hydraulic fracturing activity? Do you want to carry out a real-time data analysis? A real-time data analysis is a case where this highly high computer softwares, computer system is connected directly to the system. It's connected directly to the borehole in such a way that as the fracturing is going on, you're doing analysis at the same time. So that's the meaning of real time. You're doing the analysis as it is happening. So you are doing some kind of connection to the system where the system is actually reproducing exactly what is happening in our subsurface during the activity. But what we want to do here is to design a job. You can also do some kind of database analysis, where probably you have some data that is already stored in the FRACPRO and you want to analyze the data. But what we want to do now is to carry out a design. And to carry out a design, we have two main types of models that we could have. We have the 2D model and the 3D model. Definitely a 3D model gives us an exact picture, all-round picture of how it looks like. We can actually see the fracture half length, the fracture height, the fracture width, and all of that. We can see all of that in a picture. But for a 2D model, you cannot see that for a 2D model. So we are going to start very simple with a 2D model. So I will click here for 2D. 2D, yeah, I'll click here. Then we have different models for 2D, which I already talked about yesterday. I talked about the PKN model and the KGD model. So the most widely used is the PKN model. Of course, I showed how for the PKN model, you can calculate the fracture half length and all of that. That means if you're choosing the PKN model to model the fracture, you already know the formula that the system is using to calculate the fracture half length and the fracture width. So you don't just, because most of the times you see students who carry out maybe some kind of a mini project on something like this, and they'll just be telling you, giving you results without actually telling you exactly how the result is obtained. The system is doing the calculation, yes, but what is the system using? The system is working on some basic principles, on some physical and mathematical operations that is taking place. So you need to give this particular relationship that exists. What exactly is the system using to do this calculation? You need to give all of those equations. You need to give those equations. So we'll start with 2D model, which is a PKN model. We start with that. We'll go to next. All right, for the PKN model, we now have our world configuration. We want to configure our well ball because we need to be able to give exactly what the well ball looks like so that the system should be able to calculate the total volume of fluid that will be filled inside the well ball. Should be able to calculate that. So for the first case, they have talked about drill hole. Then the next is casing. Our drill hole, they have given the top depth and the bottom depth. We don't need to fill that. We go to casing. All right, for the casing now, you need to give the top depth and the bottom depth of the casing. You need to give the top depth and the bottom depth of the casing. You need to give the outer diameter. You need to give the weight, and then you need to give the inner diameter. So I have a data here for that. So look at the casing. All right, that's our casing. All right, if I have the data is ending at a depth of 5,300. So I will just say it ends at 5,400. It starts from 0, ends at 5,400. 5,400. Then we have the inner diameter. The inner diameter, outer diameter is 7. The inner diameter is 6.184 and the width is 29. What just happened? It's like I've deleted the FRACPRO. What did I do? Hold on a bit. It's like I deleted the FRACPRO. That software disturbs a lot. The system automatically deletes it, but all of these things are off. Why should the system delete it? Hold on a bit. Right, so when the system deletes it, you have to come here, you copy it. I will go back to my program file and paste it there. But the antivirus system is off. I don't know why. Oh, hold on. Let me shut down SmartDAV. Let me shut down SmartDAV. So SmartDAV probably may have done that. All right, is everyone are you with me? Can you hear me? Someone just
Yes, sir.
indicate.
Yes, sir.
Yes, sir.
All right, all right. So we are back on track. All right, so this is where we have fracture analysis. Next. So we have our 2D model, we have the PKN model there. Next. All right, so I said for the drill hole, you can leave it like that. For our casing, we'll put from 0 to 5,400, that is it. the outer diameter 29. This one, okay. So the thing is already indicating because I have already done the simulation. That's why you see the values here are just similar to what I have. Your own will not be the same. So you have to put this depth from 0 to 5,400 from the outer diameter is 7, the width is 29, the inner diameter is 6.18. So anytime you carry out simulation, if you want to start a new job, you have to come to new. It's just because I did not take new. That's why these values are occurring. All right, from there now, the next thing, we are still on this line, we are still on this page. We have our casing. We have indicated our casing. We go now to the surface line and the tubing. We want now to indicate our tubing. First of all, you need to know that there is some kind of a series of pipes that you have at the surface where the fluid have to flow through that pipe before it starts entering into our borehole, because you are not connecting the instrument directly. So let's take, for example, that this is our borehole. You are not connecting the instrument directly at this point up here. You may have a series of pipe. This is your tubing. This is your tubing there. You may have some kind of a piping system at the surface that is connected to the equipment, to the fracture equipment that is doing the pumping. So I have some kind of a pipe at the surface where the fluid has to flow before it gets into the system. So the first thing that I will indicate here is the surface pipe. That's the first one that I will indicate. The first one that I'm going to indicate here is the surface pipe. Bear in mind that you are at the surface. So your start depth, since the length of our surface pipe is 30 feet, we are going to take the top depth is 300 feet, not 30. The top depth is negative 300. Then our bottom depth is 0, because our 0 depth is at the point where the borehole begins. So it is starting at negative 300, then it ends at 0. The system will now recognize a length of 300 feet. Then from there now, we have our tubing now. Then you have to identify this as your tubing, as your surface line. You have to, there's various things here. You have to identify it as surface line. Then the tubing now starts from that 0 to 1,885. That's where the tubing ends before the rest of the things now continue. So you know that as the tubing ends, the rest of the rest of the equipment down now is the casing. Because if I have, let me redraw it. I have this as my borehole. So if this is my surface and I have my tubing there, if the tubing is ending at this level, bear in mind that below the tubing I still have space, because the reservoir could be somewhere around here. So there is still enough space, and this space now, the walls of the space now is the casing. The casing now is forming the wall of this borehole below the tubing, because the fluid first of all passes through this tubing. Then when it comes here now, it is touching but the casing, no longer the tubing. So you have to understand this better. So we have our surface pipe. Then from the surface pipe now, we have our tubing system. Then from the tubing system now, the next thing you have to indicate is your perforation interval. Your perforation interval, what is the top, bottom? Remember, we may have a deviated well. So for your perforation interval, it is necessary for you to give the measured depth of the top and the bottom and the true vertical depth of the top and the bottom. I've explained the concept of measured depth and true vertical depth several times. Since we are dealing with a vertical well, our measured depth and the true vertical depth, top and bottom, are the same. Then we have the diameter. We have the diameter of the perforation is 0.4. Then we have the number of perforations, because you know that generally within that interval you have but holes, because what they are doing is they have to burst the pipe, the casing, so that fluid can easily flow. So they send in maybe explosive, so some kind of a gun that is shot. Remember, a gun is made up of bullet. So it's not just a continuous perforation. Within that interval of perforation, you have perforated, you have produced small holes within that interval. It's not as if you have just destroyed the whole of that zone and the fluid is just flowing. No, we have holes within that zone where fluid can easily flow. So this number of perforations now represent those numbers then. Then from there now we have our PAP summary. This is just a summary of what we have. We have a tubing or a surface line. Then from there we have a tubing, and then we have our casing. Then from there now you see the volume of fluid, the volume of the tubing, the inner tubing where the fluid has to flow. You see that volume from here. You see the volume. Then generally you have to also indicate this particular parameter, flush volume up to. So generally there may be an error in your simulation. So if we are flushing, remember after the slurry stage, there is the flushing stage. So what you do now is, if this is our perforation interval, you flush right up to this particular level. Because if there is a little error in your calculation, if you flush right up to this level, because we don't want the flush fluid to get into the reservoir. Because if this flush fluid gets into the reservoir, where this is our perforation, it will push the propan around this zone. It will push the propan around this zone into the reservoir. Then this area now will be occupied by the flush fluid. And since there is no propan around this particular area, the stress or the overburden stress will cause it to close back. So I have a high permeable zone that I've created within this area, but closer to the borehole, there is no permeability, or the permeability is very low. So you have not solved any problem. So you cannot do the flushing right up to this perforation level, because if you flush right up to this perforation level, if there is any mistake in the calculation, the perforation fluid will get into the reservoir, and that is going to cause a problem. So we are going to flush right up to 20 feet above our perforation. All right, so from there now, that's the information that is required here. We have our casing, the surface line, the perforation. All of it is inside the Excel sheet that I have. From there, you can also view the 2D schematic of the area of the well bore. So if I click here, I have a 2D schematic. This is our borehole. This is our borehole. This is our casing. Then from the casing, we have our tubing. This is our perforation interval. This is our perforation interval. So from there now, I can take next. So everything that you need is around this area. As you are moving from next, it is moving from one option to the other. So I'll go to next. All right, from next now, there are other information that have been asked here concerning heat transfer parameters. We have the surface fluid temperature. You have to give the temperature of the surface fluid, the surface propan temperature, the temperature of the surface propan, surface nitrogen temperature, surface carbon dioxide temperature, surface rock temperature. So you have all of this information that have to be provided. We will just use this by default. We'll just use it by default because generally I don't have a data that has all of these parameters measured from the field. So we'll just use all of these parameters by default. If you have advanced thermal properties, you can also come here. Thermal fluid properties. You can come here, thermal fluid properties, thermal rock properties. I click here, I can indicate what is a thermal property of probably shale, sandstone, and all of that, because these are principally the rock types that you may have. You may define all of these parameters. But this, what we have here are the average thermal properties of this particular rock. But if they have done an analysis in that area and they have measured the exact value of this, because in all the areas you may have some slight variation. If they have measured all of these, then you can also do some kind of an adjustment to the system. So I'll go to next. All right. So the next thing now is for us to select what is our fluid and our propant that we have. What type of fluid and what type of propant do we have? So what we have here, you're seeing it in yellow is because as I said, I've already done the simulation. So I've already chosen a propant. When you open here, you will not see anything. What you do now is you come here to add new fluid to list. Add new fluid to list. You click on it. Then you have to choose the fluid that you want. Basically, we have different fluids that have been designed by different companies and all of that. So you can choose which fluid you have. We can take, for example, Halliburton. If we take like what I've used there is Halliburton. If you take, for example, Halliburton, the Halliburton also has some different types of system. It has different types of system also that you have to choose which system you want. I think I use Harbor. Then from the Harbor now, you have the various, the fluid, the exact fluid that you have. So if you see here, SG20G2K, we talk of Harbor G, 20 pounds per mega gallon of gel, and then 2% KCl. So they are talking about the amount of gel and the amount of KCl that is found. If the system, if your analysis shows that you need a fluid that has nitrogen, you have to also have to choose any of these. So there are different types of fluids that you may have there. So you may also have a situation where you have two fluids that you're using. So you can also add different types of fluids there. Like what I have here, I have two fluids there. Even though we use just the first one, if you have different types of fluids that are used at each stage, you can always indicate. You now have an area where you have to choose, because when you are doing the pumping schedule, you have to now choose which particular fluid you are using at that particular level. Then from there also, we have fluid selection, we have propane selection. So we take our propane. What type of propane do we have? Do we need? What type of propane? We can go to add new propane to list. We go to our propane. This is the various types of propane that you have. We can select if it is ceramic, the brandy sand, which I talked about yesterday, and all of that. But in this case, I have selected interpropant 2040. I explained the meaning of 2040 yesterday. We are talking about the mesh size. So we are going to use this particular propant. All right. So we go to next. The next thing now is our scheduling. We have to do the scheduling. How will the activity take place? Remember, we talked about 4 major steps yesterday. We talked about the part stage, we talked about the slurry stage, we talked about the flush stage, and then we talked about the shut-in period. All right. So these are the various steps that we will have. But before we go to the main stage, they have to carry out what we call mini-frac analysis. They just carry out a mini-frac analysis to analyze some behavior and see how this behavior will look like. And this mini-frac stage, they might use a different type of fluid within that mini-frac stage. So in the mini-frac stage, we have a circulation. We have a circulation of a fluid. And what is the fluid type? This is the fluid type that we have there, WG1136CP. Then we have shut in. Then we have a mini-frac analysis. Then we shut in before we start with our main hydraulic fracturing. We start with our main hydraulic fracturing. Remember, during the shut-in period, there is no flow. There is no flow rate. All of this data is inside the Excel, so there's no issue with it. So we have our flow rate. In this case, we have the propane concentration. You realize that at this stage, there is no propane. There is no propane that is needed. We have the volume that is injected. Then the stage length, the number, the minutes that is going to spend. The cumulative time. Cumulative time means that as you're going down, they are adding all the time there. So all of these stage 1 to stage 4, they are just preliminary analysis that have to be done before the real job is carried out. For the real job, we have the main frac part, which is our part stage, with a flow rate of 25 barrel per minute. 25 barrel per minute. Remember, this part stage, there is no propane that is added to the system. That's our volume that is needed. All of these ones that is indicated in blue means that you don't need to input them. As you input these parameters, the system is doing the calculation for you. The system is automatically doing the calculation for you. So you don't need to input all of this. So based on the volume, the system can immediately calculate the length of time. Based on the volume and the flow rate, the system can calculate the time that it will take to travel from the surface right to our perforation zone. Of course, flow rate can be translated to velocity. Of course, velocity and distance can give us time. So we have now our how many men in slurry stage? 1, 2, 3, 4, 5, 6 men slurry stage. The difference between this slurry stage now is a difference. The difference between them is just at the level of the propane concentration. At each level, you are increasing the concentration of the propane in our fluid. So we can see the propane concentration here that is increasing gradually. Then for our main flushing, for our flushing stage after the slurry, we have an injection rate of 25 barrel per minute. Then it will last the volume. You have to indicate the volume of fluid that is needed for that flushing. The volume of fluid that is needed for that flushing. Then from there, we have our shut-in period. All right, so the system now automatically calculates the cumulative time for all of the activity. So the activity from start to end will take us 129 minutes 14 seconds to carry out all of this activity. And of course, you have to indicate the propane at the level of the propane. So there are different ways in which you can do calculation. Another system is, because if you look at what we have here, we have calculate time from volume. That means they'll calculate this time from volume, or they calculate volume from time. So either you have the time and you need the volume, or you have the volume and you need the time, because the flow rate must be indicated. All right, from there now we go now to next. Okay, from here now we can run our simulation. At this stage. So we come here under run simulation, run simulator. I'll run the simulation. All right, so the simulation now, you have run the simulation. All right, so what usually happens here is they can run the simulation at each stage, and then they look at the required result and see if that result is actually what they want. If the result is not sufficient, or you are not satisfactory with the result, because you realize that the simulation has ended around stage 9, you can continue the simulation. So from there now, we can analyze. We have our fracture pressure analysis, for mini-frac analysis, entering, friction. We have our manual matching. So here we have our model output. We have our pressure match. So if I click the pressure match here, I can actually see the pressure at each level. You can see the pressure. What you have here in yellow is the net pressure. What you have here, this other color, is the slurry rate. Then this other one is the propane concentration. So you can actually see a lot of parameters. If there's any other parameter that you want to plot, you might also choose the parameter at this level. If you want to change the color, you can change the color. If you want to add any other parameter, you can add the parameter at this particular level. But for now, we'll leave this. So from here, we can already see the pressure variation during the injection process. We can see the pressure variation. Then we go now to fracture dimension. Voila, from here now we can see the frac length, how the frac length is changing with time. You can see how the frac length is changing with time. You can see how the frac width also is changing with time. So you have the frac length, the frac lower, the frac lower height, the frac upper height, the width at the perforation. They are looking now at the width at the perforation to see how it is increasing at the perforation level. because the width definitely will be varying as you move towards the reservoir. But at the perforation level, what is the width? Then what else do we have? Propan dimension. We can look also at the propan dimension to look at the propan length, the propan lower, the same thing that we have seen in the other case, you can also see for the propan. Then what else? We have the well bore profile. I can also indicate the well bore profile. This is the well bore profile to show me the variation of pressure, to tell me how the pressure varies. The pressure definitely is relatively constant within the borehole. Then this is our reservoir. This is our perforation zone within the reservoir. You can now see how the pressure is varying as you move from the well bore towards the reservoir. You can now see the variation in pressure. Oh, I've closed that. Problem. All right. So there are a lot of things that we cannot see. We cannot see the fracture profile because we are dealing with 2D. We are dealing with 2D. So we cannot see the fracture profile. If you want to generate your report, if you want to print out the report, you can come here to generate, and then you now select what exactly you want to generate. Then you go now to generate what report. Is going to generate it in the Word format. Then every analysis that you want, you can see it in that Word format. Once you store the Word format, once you go and open it, you see every analysis that you want. So anytime you do it, you can generate the Word report. All right. So we will not leave it at this level. What we have done here is just 2D analysis. For 2D analysis, you cannot see a clear picture of the fracture simulation. You cannot see a clear picture of it, like what I showed yesterday during the tutorial, during the first part. So what we will do now is we will go back to our input level. We'll go back to our input level. Then we will change this to a 3D model. We'll change it to a 3D model. We have our default 3D model, which is called the 3D shell decoupled model. The 3D shell decoupled model, we can choose that model. You realize that once you choose that model, this 2D automatically becomes disactivated. You can always come to the help button here up here to verify anything that you want to verify that you don't understand. You can always go to your help button there. You can always go to your help button. So if we choose a 3D model, we go to next. We have the same information that comes in for the casing, the surface, the perforation, and the path. The same information is coming because I have just changed the model. I have not started a new job. If I start new here, I will not see all of this information. So most of the time, you may want to work with 2D and 3D at the same time, because there are some analysis that you better see it in 2D and others that you better comprehend it in 3D. So in 3D now, all of this is okay. I'll go to next. All of this is still okay. Next. All right. So this is the major difference between our 2D and our 3D. For our 2D, we don't need all of the parameters for all of the various horizons that we need. All the various horizons that are there, we don't need all of those parameters. But for this particular case, we need them. We need them. So if I come here, for example, I have my rock properties, I have my sandstone, and this, all of these are default properties that generally remain constant for the rock, unless you have measured the property for that particular rock type and you are sure that there is something different about it. That's why probably you may want to readjust. I may go now to additional properties. I'll go now to additional properties. There are a lot of things that you have to input here that if you don't input, the system will be unable to do the calculation. So we have our reservoir pore pressure. This pore pressure is very important. It's inside our PowerPoint. I don't think that one is there, but this is the pore pressure value. We have our compressibility value. We have our pore fluid viscosity. We have our porosity. What is the porosity of that zone, of that reservoir zone? What is the water saturation here? We'll just leave it as nil, water saturation. Any other value, all of these values are just default values, but these ones are values that I inputted. Then, if you have a single layer, if you have a multi-layer, that means you want to perform hydraulic fracturing for multi-layer. Or probably even at that, we need to indicate the various properties of the various layers that we have. So what we have here, for example, if I go to my Excel sheet, which I have all of these, this is the sheet of all the various layers that we have from top to bottom. We have the sandstone layer. Sandstone is an alternation of sandstone and shale. We have the Young modulus, the Poisson ratio. We have the minimum horizontal stress, which is our closure stress, very, very important. Then we have the permeability of the various zones. Then we have the ending depth of each zone. So we have the start depth and the ending depth of each zone. All right, so if I go back to my system, we have multi-layer. Then you have to indicate all of that. I have indicated all of that, but I have highlighted the zone that I want to perform the hydraulic fracturing. So this is the zone where the hydraulic fracturing has to be performed. This is our zone of hydraulic fracturing. I have just copied the data that I have. Once you copy for pore pressure, you just come here, right click, and you take paste, you paste. You copy for porosity. You copy all of these parameters. If you have them, you just copy, you come and you indicate this. But we are going to work with a single layer for now. We are going to work with a single layer. We missed the first one, which was layers. The first what we looked at was the rock properties, and we are now at additional property. But the first one is the layers, which is the data that I have now shown you. You have to indicate all of these, the start depth and the bottom depth of all the layers, the stress, you indicate the stress, the Young modulus, the Poisson ratio, the Young modulus, the Poisson ratio. If you have the pore fluid permeability, the permeability which we also have there, you can indicate all of them here. You can indicate all of them here. So that one comes in at the level of the layers. So these are the various parameters that we have to indicate at the various layers. All right. So from layer, we talked of rock properties, which we have indicated that all of this is by default. Additional properties, you have to indicate this, because if you don't put the pore pressure, the system will not do the calculation. Especially this pore pressure, the system will not do the calculation. All right, from there we take next. Then we have our fluid also and our propan, the same as what we have in the other case. And then we have our schedule, which is the same. So once you just switch from 2D to 3D, what you will just need to input now is just this reservoir properties. What you need to input now is this layer property. You have to input these layers, you have to input this layer and this additional property, and then you can run the 3D model, because everything else will be the same. Everything else will be the same. And since you do not take new, all of these parameters now will remain the same. So I have that. Then from here now, you realize that automatically you have our fracture profile. You have the fracture profile that's now indicating. So if I click on the fracture profile, before I click on this fracture profile, let me see rock properties. If I click on the rock properties, if I come to layer, I can display this property in a log format. I can come here to layer display. When I click on layer display, all right, this is exactly what we have, a good analysis of the various properties that I have inputted and how they vary. And from there, you can see exactly where your reservoir is and where your perforation is. The red is your perforation, and this yellow is your reservoir. And this is the rock type, which is sandstone. This is the stress variation. This is the stress variation. This is our Young modulus variation, the Poisson ratio, the permeability variation, the leak-off variation, and all of that. So once you input all of that and you come to layer display, you can see all of that, this parameter. You can always change the scale of this up here. There is this player that you can use to change. You realize that once I am reducing it, the dimension, the scale is reducing. I can always reduce it like that and put it like that. So you can always reduce it. At this level, it is not really recognizable. So what I will do now is expand it a little bit so that people can actually see exactly what you're talking about. So from there, you can see the variation of all of these properties. All right. That's okay. So I'll just take my next. All right, so my fracture profile, once I click on the fracture profile, hold on. Maybe I have to rerun the simulation. All right, I have to rerun it in 3D. Voila. Rerun in 3D. I look at the fracture profile. Okay, so that's exactly what we have. So that is the fracture profile in our zone that we are going to have. You can always reduce it, increase it. So this is our fracture profile that you're going to have. And down here, you can look at this value, this particular color down here. What does it indicate? You can look at it to see exactly what it indicates. Okay, fracture conductivity. So this is our fracture conductivity, which we talked about yesterday, how to calculate the fracture conductivity. So we are seeing here that as you're moving within this area, you are having higher conductivity, and around this boundary, you are having lower conductivity because you can see the variation in color. I think we can also change it. Let me see if we can change it to indicate the. All right, we can change it up here, fracture conductivity. I can change it up here to take maybe propan location. What can we take? Propan concentration. Voila. That's exactly what I needed. Once you have the propan, this is your propan concentration. You can see exactly the change in propan. You can realize that at this particular region, you have higher propan concentration. As you're moving outward from the perforation zone within going into the reservoir, you can now see how the propan concentration is changing as a result of the color change. You're seeing the color change. But if you're writing a thesis on this, it is advisable for you to also indicate various properties, not only this propan concentration. You can have the fracture conductivity like we are first of all seeing. You can have the slurry temperature to have the variation in the temperature of the slurry. You can also have, if there's any acid, you can also have that. Propan location. You have propan location. That one doesn't tell us anything useful and all of that. So there are so many things that you can always indicate. There are so many things that you can always indicate. But the most important will be the propan concentration and the fracture conductivity. That will be the most important. We have the propan volume fraction also. We have the propan volume fraction, which is giving us a uniform color to show us that the volume does not really change that much. So you can see a varied change in the conductivity and the fracturing. So if I take this off, so this one is 3D. You cannot see this in 2D. You cannot see all of this in 2D. So if you're doing any analysis on this, you can do it in 2D and also do it in 3D because there are things that will be better in 2D and others will be better in 3D. We can see the stage profile. Once I click on the stage profile, I can see it exactly well defined. I can see it well defined. So from here, this is now telling us exactly, giving us the fracture height. From here, we have the fracture height. So we have the fracture length, the propan length, the total fracture height, and all of that. So we have a lot of things. So you realize that this is your perforation. So you are now looking at the perforation. You see that the fracturing has gone above and below your perforation zone. So you are now going to look at the water level and see if this design actually fits your design. If this design doesn't fit based on your water level, or if I intend to probably fracture all of this zone, I may continue the simulation and see what it will look like. I may continue the simulation. I may run simulator. I run again. All right, so it's telling us that that's the best simulation that you can have for that particular case. That's the best simulation. In other situation, if that's not the best, if you run, you have it changing. Maybe this region will change to 9 or to 10 and all of that. So it is telling us that that is the best simulation. That's the best result that you can actually have. You may have generate report. You may have the width profile. Let's look at the width profile to see if there's anything worth looking at there. Let me change the dimension. All right, so the width profile is just showing us exactly what we have already seen. Oh, this is our additional width. This is our width, showing the width. That's the width profile there, showing in our entire zone, showing in the entire zone. So that's the width profile there. So you can always generate the report and then you look at it. Then you can plot list what type of plot do you want on which axis. So you can always indicate the various types of plots that you want. So, all right. So that's basically our hydraulic fracturing in nutshell. That's our hydraulic fracturing in nutshell. There are so many things that what I have done here is the basic, is the main part of hydraulic fracturing. Once you have understood this, you can do anything on hydraulic fracturing. The only thing is that there are some few aspects there. There are some few terms there that you can always go to your help button to understand them better if I have not explained them. Because there's absolutely no way I can say I start from the beginning and I explain every term from every term that I see. Majority of the terms that we need, I explained them yesterday. That's the reason why I had to take my time yesterday to explain. I took about 1 hour yesterday to explain all of these concepts so that once we get to the simulation, we can just run the simulation and understand exactly what it looks like. So if you have any question, you can ask. If there is no question, we'll continue from there. So our next software that you're going to install is the Steam Kit that we are going to use next week to do acid simulation. All right, so one thing I will explain here is for this particular analysis, you don't even need to use this production analysis in order to do your production analysis. So what you will do definitely, because there are so many parameters here, so many economic data that you may not have, because they're asking you for price of things and all of that you may not have at the end of the day. So what you will do is, for you to carry out production analysis, what you will do is, once you have done this analysis, you have your fracture length, you have your fracture height, you have your fracture width. Take all of this and go back to Prosper and generate the IPR of the new well. I think we did hydraulic fracture wells in Prosper. I did that because I know that some students may want to, at your final level of the BSc, you may want to probably use this software for your research. If you're using the software, you know that after you have done all of this analysis, you have to use the data that you have at the end of the day, go back to Prosper and generate the IPR of that well, and to show that after the hydraulic fracturing, the well is now producing at a higher level. Because under hydraulic fracturing well in our Prosper, they'll ask you for the fracture height, the fracture width, the fracture half length, the fracture permeability, which will be part of the result that you're going to have. Once you generate that result, you see all of it indicated there. Once you have all of these parameters, you go to Prosper to generate your IPR. The model that you use now will not be the Vogel model or the PI model. What you use now is the hydraulic fracture model, and they'll ask all of these parameters. You input it, generate your IPR, and you now see that the well is functioning at the higher level. Because before you do that, you have to first of all generate the IPR for a situation where there is no hydraulic fracturing. Then you now see that the well is not performing well. Then after the hydraulic fracturing now, you take all of these parameters and then you now regenerate it for hydraulic fracturing well. Then you now see that the well is now performing higher because you are going to have higher productivity index. You are going to have higher AOF, absolute open flow, and all of that. So if you have any question, you can ask the question. If not, we'll meet again next week. Any question? Naomi, you have decided to join us today. Or you are still at work?
Yes, sir. Yeah, I'm at work.